welcome to lecture number 57, and in this class I will tell about reciprocity theorem, and the proof of this as an application of intelligence theorem I will utilize that one. You recall that in our last class I told you that if you have two networks A and B which are structurally same, that is their topologies are identical, these elements of course could be different in these two circuits, totally different circuits, and if you assign voltage and current polarities and their directions same in both these networks, then we found out that voltage across any element of network A multiplied by the corresponding current in that element in network B, which are denoted by these prime letters, and sum them up, they will be same, and not only same, that will be equal to 0. Now, this intelligence theorem has got several applications in the field of signal processing and so on. But so far as network analysis is concerned, as and when required I will apply that, but it is interesting to note, to prove reciprocity theorem, this particular theorem, that is intelligence theorem, can be very nicely applied to establish reciprocity theorem. Now, to do this, let us consider you have a network, for example, any network like this. Inside the box, these networks are there. Inside the box, what could be the things? It could be a networks, for example, like this, without any sources. So, network without any sources inside, and for example, this could be inside, and there could be also impedances with no initial conditions and things like that. So, if that is the thing, then these two terminals are these two terminals, and these networks inside could not be as simple as this, they could be several other elements connected, but somehow two terminals come out here and two terminals come out here, like that. Presumably, I will call it as my input terminal, or this could be my output terminal, and so on. Now, in this network, if you apply a voltage source with this polarity, suppose V1, this is network A, and these two terminals, that is, I am applying as if a voltage here. Please be with me, V1, and then if you short these two terminals, which are, as an example, this is suppose 1 dashed, this is suppose 2 dashed. So, this is 2 dashed, this terminal. So, this if I short it, then there will be currents in this circuit. I can find out this current, solve these networks, and so on. So, let this current direction, which I can arbitrarily assume as I1 in this direction, as if this all the elements will absorb power. That way we will try to apply the intelligence theorem. In this case, that is this current I am assuming I1, corresponding thing, and the current here is suppose I2, and this I will call network A. network A. Now, the question is, if I apply instead in this network, which for an example I am just showing it by a simple network like this to drive the key things, to derive the key things here. So, this is the thing. Now, suppose in this network, if I apply some voltage, say V 2 dashed I call it, and this 2 I short, the opposite thing I do, I apply the voltage across 2 2 dash and short the 1 1 dash terminal. Then can I predict this current? So, these two networks, so far as their topologies are concerned, they are identical. Therefore, for both of them, and this is suppose network A and network B, is not, are not the topologies same? Topologies are same. These parameter values are of course same as this one. That is, I am going to apply a intelligence theorem to the same networks when one of the elements have been changed, two of the elements have been changed. Here there was some voltage, here nothing was there, shorted, and things like that. Got the point? So, the network topologies are same. This current was I 2, here also there will be some current I 2 dashed, like that. Now, therefore, network B in general will look like this one, same network, that is, this is the same network as this box, same network without any sources. Inside there is no sources, without any sources. So, what I have done? I will apply a voltage here like V 2 dashed, and I will short these 2 points here. And in this network, this whole network, including these 2 input and output terminals, things are connected and their topologies are same. Therefore, I say that this current is I 2 dashed and this current is I 1 dashed. So, all quantities in this network I will denote by prime letters like this. Therefore, I will be able to apply. So, what is our goal? To find out I 2 dashed when V 2 dashed is applied here and these 2 are shorted. That is the goal. Now, to find out that quickly, what we will do is this, we will apply intelligence theorem. So, apply intelligence theorem. To network A and B, network A and B. Can I apply this? Yes, because their topologies are same. So, I will say that V 1 into I 1 dashed. So, V 1 in this branch, V 1 into I 1 dashed, this current, plus then I will complete this branch. It will be equal to, what is the voltage here? This voltage and the current of the other network I am multiplying. When these two are shorted, the voltage between these two is 0. So, 0 into I 2 dashed, is not, plus voltage of this into this current, and so on. In all the elements I have to do this. So, this is considered one element here between these 2 points. So, that one I am going to write it like this. It will be V k into I k dashed and summed over k, whatever total elements are there. So, therefore, total number of elements I have considered is to be k plus 2 summed over k. How many elements are there? Across each element I will go voltage into current of the corresponding element in the other circuit, like that I will go on doing. So, and here how many terms will be there? 2 terms there, then another k. So, total number of terms will be k plus 2. This I am telling is to be equal to the voltage of the corresponding elements. For example, voltage in this branch, in this one is 0 because this is shorted. Therefore, 0 into I 1 and all are absorbing power, is not? That is how I assume this direction of the current. So, 0 into I 1, always be consistent with that, 0 into I 1 plus then this term I will first write, that will be V 2 dashed into I 2 plus V k dashed into I k summed over all the elements here in the network present, okay, summed over k. So, first term, second term, then the k values here will start from k equal to 3 and so on. So, this is how this is what Telegen's theorem tells us, that this will be true. Then you see that, or I will write that V 1 I 1 dashed, this one is of course 0 plus this one summed over k V k into I k dashed. What will be V k? If it is purely resistive network, I can write it as R k into I k. This is my V k, because no source is involved. So, across each branch there will be voltage drop. So, into I k dashed, and on the right hand side you will get this is 0 plus V 2 dashed into I 2 plus this term, this will be V k dashed, which will be equal to, because this network has not changed, exactly same as this with same parameters. So, parameters have, elements have changed only in this in these 2 branches, you got the point. So, inside it is same. So, R k same R k into I k dashed and into I k summed over same k. These 2 terms, if you see they are same, R k into I k dashed, this is also R k into I k dashed into I k, they are same. Therefore, they will cancel out, these 2 terms will cancel out, and you will be left with V 1 into I 1 dashed is equal to V 2 dashed into I 2. It is needless to say that if this impedance, only condition is that this internal network, here there should not be any sources present. However, it could be impedances ZS, is not. It could be ZS also, because V k can be written as Z k into I k. So, whatever resistances I have put, this could be replaced by ZS. That is, the energy storing elements may be there, but with the condition that they are not having any initial currents. That is the thing. Anyway, we have got this very important results, which says me that if you apply V 1 here, this is I 1 will be the current here and I 2 will be the current. So, what was my problem? To determine all things I have written correctly. So, V 1 I will say that I 2 by I 1 dashed, I 2 by I 1 dashed is equal to V 1 by V 2 dashed. This way also I can write it. Or I can also write that I 2 I want to find out, it will be V 2 dashed by I 2 is equal to V 1 V 1 by V 2 dashed into I 1 dashed. Is not? If I have applied a voltage V 1, current was I 2. If I apply a voltage V 2 dashed here, what should be I 1 dashed? I 1 dashed also can be written in this way, it will be V 2 dashed. I think this is the final thing I should concentrate upon, into I 2. So, what was my problem? My problem was, if I apply V 1, I noted this current to be I 2, that is known. What will be the current I 1 dashed when you apply V 2 dashed here? It is this value, I 1 dashed will be V 2 dashed by V 1 into I 2. If these two voltages happens to be same, if V 1 is equal to, that is this voltage V 1, same voltage if you apply as a special case V 2 dashed, then we note that I 1 dashed, this current will be same as I 2. These two are same, you can cancel it out. So, I 1 dashed will be equal to I 2. As a special case, that was more general an expression. So, what is the conclusion? Conclusion is that if you have a network, linear, bilateral, need not be linear networks like that, and here is two terminals. Here you apply a voltage with this polarity V 1, and here suppose these two are shorted, and this current is I 2, is not? V 1 applied, I 2 current flows. Then the same network to this pair of terminals, if you apply a voltage V 2 dashed, which happens to be equal to same as V 1, I am telling, if you apply same voltage, then if you short it, then this current, which is equal to I 1 dashed, because this is the element I 1 dashed, this will be same as this current I 2. This is the reciprocity theorem. In general, if this it is V 2 dashed, this is true if V 2 dashed is equal to V 1. Otherwise, also I will be able to calculate this current I 1 dashed is equal to, it will be I 1 dashed will be equal to V 2 dashed by V 1, V 2 dashed by V 1 into I 2 in general. So, if you apply to this terminal a voltage 2 times, then this current will be I 2, and this is called reciprocity theorem. It will be clearer if I do a very simple, but useful example to highlight the concept. Suppose you have a network. What do I mean by this? You have a network like this. This is suppose a 30 volt source you have applied, and the networks are, this is suppose 0.6 ohm, this is 4 ohm, and here it is suppose 6 ohm. Suppose here between these two terminals I have applied 30 volt and I will short this. So, this is network A, you know that example. Then I am asking you what will happen 0.6 ohm, this is 4 ohm, this is 6 ohm, and here I will apply this voltage 30 volt, and how much will be the current in this branch. This is called reciprocity theorem. If you short these two, there will be some current here for a given applied voltage between these two terminals. Then to these two terminals, if you apply that same voltage, then what will be the current? The calculation of currents are very simple. I have taken the figure. If you solve it, it will be 4 ampere here and 6 ampere there, and here it will be 10 ampere, is not? It will be 10 ampere. So, I am predicting that if you apply same voltage to these two terminals where 6 ohm is connected 30 volt, then this current in this direction I am predicting it will be 4 ampere. Now, this I have shown 10 ampere like this. It gets reversed. Now, this current in this circuit, if I solve, how much will be this current? 10 ampere. In this direction, forget about your intelligence theorem conventions. This will be the exact current 10 ampere, 6 ampere, 4 ampere. Now, to be consistent with that, you can only say this is minus 10 ampere flowing into this. This is your the value of I 1. Okay, that way if you want to think, this is this one, this I note it down. Then I will say that this is minus 10 ampere and this is 4 ampere, that is fine. Now, if you apply 30 volt here, what will be this current? Top to bottom 4. So, minus 4 ampere here. So, from bottom to top it will be 4, that is. Let us solve this circuit individually. Okay. So, what will be this current independent of this intelligence theorem? This current will be, first you calculate this current, that is how much it will be? This current will be total current 4.6 ampere, that is do series parallel this thing. Then what will be this current? 4.6 will get divided into two parts. So, 4.6 into 4 divided by 4. So, this will be 4 ampere, is not, this will be 4 ampere from bottom to top. Therefore, this was 4 ampere this way flowing, and if you apply 30 volt here, 4 ampere from right to left it was flowing. Now, if you maintain the polarity of the supply voltage 30 volt here, this current will be, because that was the derivation, this will be 4 ampere. Is that clear? So, what I am telling, in the second case I need not find out series parallel combination if I know this particular theorem. I will even say that if suppose to these terminals 2 and 2 I will short these two. This information is known to me. This is 30 volt, this is 4 ampere this way. If this information is known to me, suppose these two I short and here I apply a 10 volt source. Got the point? What will be the current? I need not solve the circuit once again. It will be how much? 4 by 3 ampere. Why? Because that current will be 4 and voltage ratio is 1/3. Instead of applying 30 volt, I have applied 10 volt, V 2 dashed by V 1. So, this current will be V 2 dashed 10 by 30 into this current 4 ampere in this branch. So, 4 by 3 ampere. You see the usefulness of this problem, this particular theorem. If you apply across two terminals a voltage, then current in some other branch you calculate it. Then you need not once again resolve this circuit when you apply across these two terminals a voltage and other two terminals where you connected voltage earlier put a short circuit there. These magnitudes of current remain same, or if you apply any fraction of that voltage here, by virtue of this relation I will be able to calculate that current. So, this is called reciprocity theorem. This is of course, one can apply it for any complicated or even AC circuit. For example, I say that I connect a voltage here where these are impedances, not just resistances Z1, Z2, Z3, and these two are the terminals I have identified and these two I have shorted. So, I will solve this network for this current, I will solve, that is I 3, I will be able to solve this. Complex impedances are there, suppose sinusoidal applied voltage is there V 1, I will get this current I 3 here. Then I am telling the same network Here you apply a voltage V 2 AC voltage, because complex Z 3 and Z 2. Then this current in this branch, you need not resolve the circuit. It will be equal to this V 2 by V 1 into I 3, where I 3 was this defined, is not? This is the crucial thing, V 2 dashed by V 1. So, V 2 dashed is this one, V 2 here. So, be careful about whether I call it V 2 dashed or V 2, it does not now mean. Now, after learning all these things, I will say, okay, here is a circuit, you apply a voltage between these two terminals V 1, note down the current in this branch, its direction. Then if you apply instead this voltage V 1 there, some other voltage V 2, then you can find out the current in this branch efficiently. So, it can be applied there, sometimes it is very useful. Similarly, in a network, if you apply a current, this I leave it to you. Suppose we have a network like this, I mean extension of this. Suppose you have a network like this. Suppose you connect a current source here instead of voltage source I 1s. Then calculate the voltage between these 2 points here. There will be some voltage available. Then whatever is this voltage, say V 2, you calculate, solve this network, these are impedances, suppose Z 1, Z 2, Z 3, Z 4, Z 5. Calculate the voltage with this plus this minus. Then if you open circuit this one, just opposite to that of this. Here if you apply the current source I 2s, I 2, then same current if you apply I 1, then I am telling the voltage you will get between these two will be same as this V 2, that is the whole idea. Therefore, solve problems, we will solve some problems and upload it. Therefore, reciprocity theorem, I hope you have understood simple ideas that in a network, linear network like this with no initial conditions, of course, if you know, if you have applied a voltage V 1 between 2 points and you are examining currents flowing through another 2 points when they are shorted, whatever is the value of the current, instead of applying voltage here, if you short it and connect the voltage source here, in this branch the same current will flow. With this I conclude the what is called the reciprocity theorem and intelligence theorem as such. There are several interesting problems, you try to apply wherever possible. Nonetheless, we will solve some problems and upload it as and time, as and when it is required. Achha, now another small theorems which I must tell to complete this one, that is called maximum power transfer theorem. Maximum power transfer theorem. Okay, this maximum power transfer theorem we will take up in the next class.